Okay, well, thank you very much for inviting me here. So I'm Matt Shaw, and I'm at JPL. Most of you probably know JPL is an FFRDC in Pasadena, California, which has been around since 1936 and has been run under contract with NASA since 1958. Okay, so what I'm going to be talking about today are waveguide-integrated near-infrared MKIDs. And you guys heard about MKIDs, I believe, yesterday with Ben Mazine's presentation. And these are a building block towards an on-chip cryogenic spectrometer in the near-infrared, I'm going to argue. This is, at the moment, still just TRL-1, and it represents the first step towards a practical, robust technology for making a low-cost, low-mass cryogenic spectrometer in the near-infrared. So just to back up for a moment, my background and experience at JPL is primarily in the development of superconducting nanowire single photon detectors. So I'm going to tell you a little bit about these as well. These detectors are, if you're not familiar with them, superconducting detectors that are useful for time-correlated single photon counting. And they work from the UV out to about 5 microns. They are very efficient. They have over 90% efficiency at 1.5 microns, which, if you're familiar with off-the-shelf single photon counting detectors, is not easy to do with semiconductor devices. They have 100 picosecond order time resolution, sub-hertz dark count rates, 40 nanoseconds of dead time. We've made them in arrays as large as 64 pixels. They have a 1 Kelvin operating temperature. And the primary applications of these devices are for space-based optical communication and also for quantum optics experiments. The way these detectors work is actually very simple. All this detector is a superconducting wire, which is meandered across a substrate. When a photon hits the wire, it creates a little hot spot, causes a few Cooper pairs to break, and causes the wire to go into the normal state. So the impedance switches from 0 ohms to a few kilo ohms within a matter of picoseconds. This basically gives all of these nice performance that you see here. And in particular, the thing that these is very nice is that we're able to get very high efficiency and detectors which don't depend much on the actual bias current. So this is what really allows you to scale these things up to arrays. And we've been working on this for a variety of different projects. Most of our work is that's funded by STMD is for deep space optical communication. So we're very interested in supporting the future optical communication technology demonstrations. We're making large format SNSPD arrays that are as large as 320 microns on the ground. And we've been developing free space coupling to these arrays, and we've really made a lot of progress just in the last couple of years, going from single pixels to large arrays. We also are involved with a project to do quantum key distribution, which is DARPA funded, and we have projects to develop SNSPDs that work at higher temperature, that are optimized to work in the UV. We do a lot of work developing cryogenic readout circuits, and also devices that are integrated with on-chip photonics. And that's what I'm going to be talking about today, and talking about how you can also extend this SNSPD concept to waveguide-integrated MKIDs. So briefly, we've developed this technology where we use we've taken SNSPDs and we've tried to put them into an integrated photonics platform. So this is useful because this allows you to bring superconducting detectors into the world of on-chip photonics. The detector itself is very simple. It's basically just, instead of a long meandering wire, it's just a little hairpin that sits on top of a waveguide. Light is then coupled from the waveguide up into the detector. And the thing that's interesting about this, I mentioned before, these detectors have no intrinsic energy resolution. So if you want to be able to resolve energy for any reason, you can integrate them with some on-chip spectrometer, something that gives you some energy selectivity. So here's what an example of what this thing looks like when it's all packaged. We've developed these cryogenically self-aligned fiber to waveguide couplers as well. We have SNSPD integrated with a ring resonator to demonstrate some spectral selection. And so it's a little hard to see, but here's this little hairpin of a detector. And these things really work. We see this nice behavior of a well-functioning device, as I showed before, where we get this saturation of the efficiency with the bias current. We see that the detector does, the resonator does well to screen the detector from dark counts. And it really does select out frequencies. These are the different modes of a single ring resonator. And you see we're able to get good frequency selectivity over a 100 picometer bandwidth. So, OK, why would you care? Why would you want to make SNSPDs integrated with on-chip photonics? Well, there are some things you can imagine doing. You might want to make wavelength multiplexed receivers for quantum communication. That's a good application for an SNSPD because the SNSPD is very efficient and has high time resolution. You might want to, similarly, for quantum communication applications, do on-chip heralded single photon sources. That's also a good application for the SNSPD. Okay. But for on-chip cryogenic spectrometers, an SNSPD is really not what you want because the SNSPD has a lot of time resolution, which you generally don't need in a spectrometer. And that time resolution costs you a lot of bandwidth. So if you want to have a lot of channels, you really want to get some multiplexing in there. And a good way to get that is to throw away some of the time resolution and turn your waveguide-integrated SNSPD into a waveguide-integrated MKID. So I don't need to really belabor the point of how MKIDs work, I suppose, because I think you heard about this yesterday. The MKID is a very similar device to the SNSPD in a way, except that instead of, in the sense that a photon comes in, breaks some Cooper pairs, but instead of using it to halt a flow of current, you measure a change in the kinetic inductance by embedding it in a resonator. And then you look for the frequency of the resonator to shift as a sign of your signal. This is just a summary saying that what MKIDs can do. Because of this frequency multiplexing, you can send a comb of tones, and you can read out thousands of MKIDs through a single RF feed line. You can get quite good NEPs and do single photon counting, as you heard yesterday. And these have undergone more than 10 years of development now in astrophysics. So what we've tried to do is to develop MKIDs that can be integrated into waveguides as a first step towards making this kind of cryogenic on-chip spectrometer. So what we've done is very similar to the SNSPD. We have a waveguide where light is coupled in. Then it travels along the waveguide. It gets absorbed in this relatively tiny inductor. Because the inductor is small, we have a big capacitor, which serves as our resident LC circuit. And this work has been funded by STMD's Center Innovation Funds. So basically, the concept is that light comes in. Here's a simulation of an optical mode. And then it is evanescently coupled into the metal. And it's adiabatically, the energy is adiabatically transferred in. So over an absorption length of about 11 microns, or about 10 microns. So this work, we really just started it a few months ago. So we don't have data yet, but we're very optimistic that this is going to work well. So OK, so why make a cryogenic spectrometer on chip? What am I talking about here? So in the near infrared, like defined as 1 to 5 microns, cryogenic spectrometers in principle offer orders of magnitude higher sensitivity than a 300 Kelvin spectrometer. So this is a simple calculation which considers an ideal channelizing spectrometer with R of 1,000 operating over 1 to 5 microns with perfect detectors. So what I'm interested in this graph is just what is the fundamental limit due to photon shot noise that's imposed because I'm exposing my system to room temperature radiation. So there's two components. This component here is due to the fact that your spectrometer itself is at some temperature. Your grating is itself emitting background. And this component is due to the background light that you're coupling in from the top. And what you see is this blue curve corresponds to the 5 micron end. if you're looking at a room temperature source, a 300 Kelvin source, you get about a factor of 20 improvement in sensitivity if you use a cryogenic spectrometer, even at this wavelength range. If you go to a colder source, things get even better. Here we go. So this is looking at a 100 Kelvin source. So if you're actually looking at a source which is cryogenic, then having a spectrometer which is cryogenic can really buy you even more. So here you see you go from 10 to minus 14 down to 10 to minus 20 at the 5 micron end. So you're really getting 4 or 5 orders of magnitude. And MKID, we said, has an NEP that's reasonable to get 10 to the minus 19. So you can actually do single photon counting in the mid-infrared if you have a cryogenic spectrometer. And the point is that there are a lot of applications, in chemistry where people are operating very far from the single photon limit. And the reason it's not practical is that they don't have a cryogenic spectrometer. So this curve just shows how it changes with frequency. OK, so why doesn't everyone have a cryogenic spectrometer in their lab? The reason is that cryogenic spectrometers they require cryogenic alignment of bulk optics. They're generally speaking very costly, very complex instruments that are used for big science, right? These are things that are used on instruments for telescopes, space telescopes, things like this that require years of engineering and cost millions of dollars. They're generally things that chemists can't afford in their labs. And they're usually used at longer wavelengths where cryogenic operation is not a luxury that buys you a few orders of magnitude, but an absolute necessity. So the question that we're asking here is, what if you could invent something that gave you this signal-to-noise advantage of a cryogenic spectrometer, but that didn't require this very complex, costly instrument, something that you could integrate on a chip and fit into your hand? Well, it turns out that people have accumulated a lot of knowledge from the world of on-chip photonics for the telecom industry. In the telecom industry, people want to do dense wavelength division multiplexing, and so they've developed powerful tools. They've developed this is just one example of planar concave grading. There's also arrayed waveguide gratings, other things. But there's a lot that can be leveraged by extending this kind of telecom technology into the mid-infrared. So what would you need to actually build such a thing? Well, you need to have waveguide-integrated detectors that can operate from 1.2 to 5 microns. You need some kind of fine spectrometer element that has at least R of 1,000 to be useful. You need some, generally speaking, coarse spectrometer element, because if you have one of these on-chip spectrometers, chances are it can't operate from the entire wavelength region, 1 to 5 microns. So you need to break things down into octaves. And you need some efficient way of doing broadband coupling from fiber to waveguide. Telecom things are usually inherently narrowband, so people have not really tried to optimize things on chip over very wide bandwidths. So that's a real challenge when going to the mid-infrared photonics. But there's no reason, due to Maxwell's equations, it can't be done. You also need good low-loss mid-infrared waveguides. There are solutions for all of these problems. You can use waveguide-integrated MKIDs, they certainly work well from 1.2 to 5 microns and give you very, very high performance. It's interesting to think also about integrating this technology with semiconductor detectors. If you looked more carefully at that curve I showed you, the real advantage of the cryogenic spectrometer, you really get almost all of that advantage by the time you're at 77 Kelvin. So if you have some, I don't know, maybe Mercatel semiconductor detector array or something else that can operate at, in the 80 Kelvin region, then it might be very interesting, theoretically, to have that as well. If you need for fine spectrometer elements, there are a lot of things you can do. You can make these shell gratings, planar concave gratings. You can make arrayed waveguide gratings. And there's also schemes to do on-chip on-chip FTS with no moving parts, although that has a big signal-to-noise penalty, so that's generally not a good idea. There are also coarse, you need for coarse elements. There are nanophotonic mode splitters, or you can just use a big grating. And there have been nanotapler couplers that have been developed and that could be adapted into the mid-infrared, given what's already happened in the telecom industry. And there are certainly good substrates like silicon on sapphire that work through this whole 1 to 5 micron region. And these substrates are also very interesting for MKIDs because they don't involve any amorphous dielectrics, which is a big source of noise in MKIDs. So if you so silicon on sapphire is an ideal substrate material. So OK, just in summary, this technology is sort of in the loose talk stage. So there's considerable research necessary to turn this into reality. But there's no reason in principle it can't be done. So yeah, I think that it offers orders of magnitude more sensitivity. And the goal or the vision is to make a cryogenic spectrometer a practical instrument and a practical technique for small spacecraft or laboratory experiments, and take it out of the realm of big science. So if you were going to try to commercialize this and take it into some sort of market, I think that there's a lot of potential applications in laboratory chemistry. So there are a lot of spectroscopists out there that are putting more power into their samples than their samples can handle because they don't have enough sensitivity. And as I showed in those graphs, the gainer is particularly strong if you're looking at cryogenic samples anyway, which some spectroscopists are for reducing thermal broadening and or just studying ices and things. In principle, you could also, I suppose, argue that it's useful for space-based astrophysics. For example, one application is doing solid-state spectroscopy on interstellar ices, trying to find out if the ice is amorphous or crystalline, is an open problem, long-standing. And if you could somehow integrate it with detectors at 77 Kelvin, it might be feasible for some CubeSat mission. And then theoretically also for ground-based astronomy, you could do simpler, cheaper cryogenic spectrometers. So I'm Matt Shaw, and you can contact me if you like. And in summary, I think cryogenic spectrometers offer the potential for orders of magnitude improvements. On-chip photonics can be used to actually turn this thing into a practical, useful device. And these waveguide-coupled MKIDs, which we've developed under the SIF funding, or are developing, I should say, under the SIF funding, are the first step towards achieving this, this goal. So, thanks. Any questions? Yes, sir.
What are the limits on the spectral resolution? Can you push this up to 10,000 or 100,000?
It probably could be pushed up to 10,000. If you look at what people have done over narrow bands in the telecom, people have pushed it to, about 10 gigahertz of spectral resolution. So that would correspond to, R of 10,000, something like this. To go to truly high resolution, you need very high. You need a lot of detectors, for one thing. So you need 100,000 detectors, which I suppose may be possible with MKIDs. And you also, to go to R of 100,000, your spectrometer needs to get bigger. Your on-chip spectrometer, instead of being 1 millimeter, might need to be a centimeter or something like this. And so 10,000, I think, is very doable in terms of the photonics. 100,000, it might be pushing it.
What is the loss of the integrated waveguides at these wavelengths?
Yeah, it's a good question. So it's not the loss in silicon and sapphire is not too bad over the scales that you need to make. I mean, at 1550 losses, it's possible to get below 1 dB per centimeter. It's probably about 10 times that in silicon on sapphire at 4 microns. So it's true that you're going to take some loss by doing this. And typically, when you make one of these spectrometer elements, there's also you have to consider how reflective you can make the facets. People do things like doing integrated DBR facets or embedding gold, but typically there's some, 5 dB or so of loss just across the spectrometer. So it may be hard in practice to get the total throughput of the spectrometer above 10% or something. So that could be another, disadvantage. But if you are gaining orders of magnitude of sensitivity.
What about the cryogenic cooling systems themselves? How would you evaluate their state of readiness and where they're headed and what the practical issues are?
Yeah, well, I think that if you're only trying to cool a sample package, right, it's much simpler than cooling a bulk spectrometer. Currently, there are commercially available cryocoolers, which can get to sub-Kelvin temperatures without much trouble. You can take a pulse tube cryocooler, which is commercially available, and add a commercially available helium-3 refrigerator insert. And for SNSPDs, there are companies trying to commercialize this and successfully commercializing this so that the user can have a 1 Kelvin fridge which sits in a rack and is transparent to these things. The dream would be to have a sample package that has a fiber or a handful of fibers coming in on one side and a few RF cables coming out. So yes, it's true that you need a cryocooler, and it's true that you need a helium-3 fridge, and probably that's going to cost you $100,000. But it's not like building a cryogenic spectrometer instrument on a telescope or something where you have to cool everything down and make sure that everything stays aligned as you cool it down. Any other questions? Yes, sir.
How easy is it to do on-chip calibration?
To calibrate the detector, you mean?
To calibrate the frequency, and if you really could push this up to 100,000 or 100,000 on chip, then you could do rate velocity surveys in your backyard.
So you want to calibrate, you want to have a calibration source on chip?
Yes.
Well, I mean, in principle, you could imagine having a laser, but maybe on an adjacent chip or something. I mean, it's hard to imagine dissipating the kind of power into a chip that a laser requires if there's also superconducting detectors, on the same silicon substrate. But I suppose in principle, you could have a laser of very stable, very well-known frequency somewhere nearby. Other questions? Thanks.